Especially like right after it comes out.
That's what it is.
Yeah. Well, my advice, you should have at least 2 hours free. So for those things.
I tend to wait in my This is
Something okay, this giant power bank. Like a tube is swung up. There's a tube. Yeah.
All right. Well, let's go ahead and get started. As you guys know, I'm starting to grade the exam, so I think I can get at least I think I can get all of that done over the weekend, in the worst case. So it's all gonna be done. I think most of you have a general idea of how you did in the test. So the number is really just to confirm your suspicion. I'm trying to give partial credit as much as I can. For one of the questions where the answer is $L1, the dollar is worth half the points, and then the L1 is worth the other half of the points. So I try my best to give partial credit. Anything that shows signs of understanding the material is going to give you some credit. Are there any questions regarding the homework assignment? How many people did the extra credit part implementing main in assembly? A few, okay. All right. Well, just the attempt to do so, is going to give you some insight about assembly language programming, particularly how C code translates to assembly code. So if you haven't tried that, just kind of think about it, look at the code, and then think about, okay, do I know how to implement this feature? Do I know how to implement that feature? Just do it case by case and see how much you already understand. All right, so we are already starting to talk about C structures in assembly code, and then yes.
With the test, are you going to add the 2 extra credit?
Yeah, 2 questions will be considered extra credit.
Okay, that's good.
So even though you have 8 questions, the baseline would be 6. If you get 6 perfectly done, then you have 100%. If you get 8 over 6, then the extra will be extra
So I
credit.
might not fail this class after all. All right, guys. Yeah.
You just broadcasted that to YouTube, by the way.
But next time, bring a guitar or a musical instrument. That.
And I'll get extra credit. Okay,
Get a little, make a little jingle. Every time you say that, make a little jingle for that. It's starting to look like more and more like those late night shows. Where.
The late night.
Yep.
This is the best that you can do.
I don't think I can be successful as a comedian, so kind of gave up on that idea.
I like the Star Trek jokes. They're good.
Most of the
Most
of the jokes are unintentional, so they're accidental. All right, so let's go ahead and finish up this topic because we are really pretty much done with most of this stuff. So we'll go ahead and take a look at this part here. All right. So we are done with finding out the member offsets and user structure in assembly language code. Are there any questions before we move on to talk about how to return a structure? No questions? So you guys are all ready, to to
I'm
deal
not
with
ready, but I don't want to hold everything up. So.
to return the structure. So let's go. Okay. So let's go to section 2.4 and deal with this part here. Okay, so here we have a fairly simple structure, called it struct X. It has 2 members, one is P and one is Q. The fun part is, what do we do when we have a subroutine like this one? The return type of make X is not a pointer to a struct X. It is a struct X itself. So the question is, how do we do it? Particularly, what is this particular statement doing? Now, what is happening here is the C, from the caller's perspective. This is from the caller's perspective. So what the caller does is, the first thing is, it will reserve the space to store and extract, or struct X in this case. So by subtracting the size of struct X from the stack pointer, we are moving the stack pointer down by the size of the structure and therefore reserving that space. It's going to move ESP to EAX so that we can push that later on. And then it will push the usual parameter because we have 10 as the second parameter and we have 23 as the first parameter. Those will be pushed on the stack. But now we have something that is extra. We have EAX also pushed on the stack. EAX, which is the address that we have just reserved, is not one of the parameters, but it is pushed on the stack, and this is a GCC convention. Are we doing okay so far? Mm-hmm. It has an implicit, first parameter, which is the address of the space to store the return value of this particular subroutine. Okay, and then make X is called. Okay, so when we get to make X, the way we label our parameters has to be changed a little bit in this case. Old EBP is still pointing to, EBP is still pointing to its own old value, so that part has not changed. Return address is still right after that because there's the call instruction. But now we also have the return value address, and that's taking the place of the first parameter. The first parameter becomes return value address +4, and then the second parameter becomes P1 +4. In other words, everything got shifted by 4 bytes because we have an implicit parameter that is not spelled out in the C version. Are we still doing okay so far with this code? This part is from the callee's perspective. From the callee's perspective, this is how we handle the displacement from where EBP points to the various items on the stack. The one item that is extra in this particular case is where we store the return value. Is that okay? Okay. And we also want to allocate for our local variable. In this case, our local variable is just one single struct X, which we call V. So when we allocate that space, we have to say V, or the first byte of V, is going to be X size many bytes below old EBP. Because it is our local variable, so it belongs to the negative side of old EBP. Our last local variable is our only local variable. I only use this one so that in my code, when I reserve the space for local variables, I don't have to refer to V itself. I only have to refer to last local var, and that's just a little handy feature for myself. Are there any questions about this? We'll do one example later on. We'll just actually go ahead and make one example similar to this. All right. So what do we do when we actually have the return statement? In other words, what do we do when we translate this particular statement? Now, if V were a scalar, like an integer or even a 32-bit floating point number, we know it's easy. We just copy that to EAX, and EAX becomes our return value. But that doesn't work when you're returning an entire structure. When you're returning an entire structure, you have to copy our local variable V to the space that was reserved by the caller. So the way to do that is to call memcopy. And memcopy, if you want to find out how to use memcopy, you can just say memcopy. It takes 3 parameters. The first parameter is a pointer to the destination. The second one is a pointer to the source. And the last one is the number of bytes that we want to copy. So when we try to do something like this in assembly, we have to push the same parameters. We're pushing the last parameter first, which means we are passing the number of bytes to copy, which is X_size. We are pushing the address of the source next, and this together will push the source address, which is the address of local variable V. And then we want to push the destination address, The destination address is return value address itself. Is a 4-byte thing on the stack pushed by the caller. So this is how I know where I'm supposed to store the return value. Once all three parameters are pushed, we just have to call memcopy and have memcopy to deal with the details of copying from V to that unnamed space in the stack reserved by the caller. And then we have to add 12 to the stack pointer to reclaim that the 12 bytes that we have used a little bit earlier for memcopy, and it's all done. So this is how we return a value that is a structure itself. It is important to note that in GCC assumes the callee to deallocate the pointer to the area reserved for the return value. This is not difficult to do, although not impossible. Using familiar instructions, this can be done by the following code at the end of the callee in place of the return instruction. But this is really kind of obscure because it kind of defeats the whole purpose of having the caller to deallocate anything that it allocates. In other words, in this particular case, this space here is supposed to be deallocated by the callee and not by the caller. So the way you do this is you have to, by the time you clean up the stack after yourself, after you pop EBP, then you have to retrieve the return address into EAX. And then you add 4 to the stack pointer, and then you have to jump it to do it that way. Basically, you're telling the caller that there are 4 bytes that you have deallocated already, and it doesn't have to deal with those 4 bytes. It's a convention. If you don't do it, it doesn't work. Are there any questions? And the other way to do this is to use return $4, which is basically saying, we are returning like normal, but we're also deallocating 4 extra bytes when we are returning as well. When you return back to the caller needs to do the following. It only has 8 more bytes to reclaim from the stack for the parameters, and it has to move the stack pointer to EAX because EAX. Okay, I might have. Oh, never mind. I'm making a snapshot of the stack pointer into EAX because later on I have to push EAX on the stack. And then you want to push the 3 parameters to get ready for another memcopy. Now this is assuming your caller is doing a particular thing. Let me see. The caller is trying to finish this assignment statement. So that's why we have another memcopy from the caller's perspective in order to copy the return value of the make X call to the address of W itself. And that's what the second memcopy is for. Any questions about that? And this memcopy is done from the caller's perspective. Are there any questions?
I'm gonna give you the poker face.
Poker face. We call it the Mr. Lestrange face.
The what face?
Mr. Lestrange, Michael Lestrange. He uses this icon to represent himself, as an avatar. So it's just this, which I think is the poker face. Okay. Any questions about this one? I mean, the topic that we just talked about, how to return a structure from a subroutine. No questions? Yep.
We're going to do an example of this, you said?
Yep.
I'd like to actually see how that works on the stack.
Okay.
Along with an example, so we're kind of going through it line by line.
Okay, let's go ahead and write the program just to do this. And I'm just thinking about what the program is going to do for illustrating this point here. So we'll do the C code first. The C code is okay. Let's deal with complex numbers. Is everybody does everybody feel comfortable with complex numbers? More or less. Okay. Well, it doesn't really matter because I'm just using that as as an example. So we'll have count include stdio.h, and then I'm going to define the structure complex. And I should probably do that in a header file. I'm going to take a shortcut today, so I don't really go through the trouble to define the structure inside the header file and have another program to generate the include file and so on. Okay, so and I'm only going to use integer because I don't want to deal with floating point numbers. So we have the R component, which is the real number, and we have the I component, which is the imaginary number part of a complex number. So now we can start to write stuff like this. Struct complex, the return type is a struct complex itself, and we can figure out how to do multiplication for complex numbers. And we will take two structures. We'll call the first one X, and we'll call the second one Y. And these are passed by value. In other words, the parameters are passed by value also. What we are returning is going to be a struct complex, but I don't have access to the return area inside the C subroutine, so that's why I need a local variable like this to store the result. So result.I is, I think it's x.r times y.I, and then plus x.I times y.r. Is that right? For complex numbers? You cannot remember? Sounds good? Okay. I know about the real number part. X.r times x.r minus x.I times x.I. Because I squared is -1.
Should be a Y.
Sorry?
Should be a Y.
Oh, should be a Y, that's right. There we go. Yeah, one should be a Y too. There we go. And then return result like that. All right, so we'll give it a try and write our main subroutine. And inside the main subroutine, I will have two struct complexes. So complex, I'll give it a name A and a B. So A.I, I'm just doing the initialization here. A.R equals 2. A.I is -2. B.R is 1. B.I is 3. And now we can have our own struct complex C. So that C equals to multiply complex, and then we're using A and B to do the calculation. Print F, C.R equals to %D, C.I equals to %D, new line, C.R, I, 0. All right. So what do you think it should be printing according to the code that we are writing? The R portion is R times R, which is 2, minus I times I. But this is the -2. -2 times 3 is -6, but we want to subtract that much. So we end up with 2 plus 6, so the R portion should be 8. The I portion should be these two, the product of these two, plus the product of these two, so I think it should be 4. So the output should be, the real portion should be 8, and the imaginary part should be 4. No? Yes? Kind of?
Sure.
Okay. I think that's what it's supposed to do. Okay. So we'll test the program in pure C code first, and then we'll try to implement it in the sample. GCC-O complex C, and it prints 8 and 4. Okay, so that's good. We know what it's supposed to do. Now we need to go implement the subroutine. And particularly, we want to implement this particular subroutine. We will keep this much as our prototype, and then we'll comment out the rest using pound if0. We'll take this code from line 11 to 17 and write our subroutine, mode complex dot. Well, dot lowercase is fine because I'm skipping the trouble of keeping track of the offsets.
Just a little C question. Why are you doing the pound if 0 instead of like a slash asterisk or something like that? Is that better?
Well, the reason, okay, let me switch back here, paste it first, so I don't forget. Okay, it's because if inside here I have, okay, let's, to illustrate why I use this feature, if I use, comments inside the code that I want to comment out, then that's not going to work anymore.
Right.
But pound if0 still works. Because pound if0 is a preprocessor feature. It bypasses all the syntax of C completely. It can also be nested. So if you have some code inside, that is already commented out, and you have another pound if0 that try to comment out even more code, it can be nested without a problem. So that's why it's just more versatile compared to slash and star and star slash.
Yeah, I like that. That's great. Wish I learned that last year.
Well, the other thing you can do with pound if0 is you can use conditional compilation. So instead of doing just this, you can also define an else. So this way, it gives you a quick way to alternate between two different chunks of source code. So in case you want to test it, you don't have to, you can just change the constant here from 0 to 1, and it immediately switches over to the other piece of code. So it's a handy feature. All right, so now it's time to implement this all in assembly. So let's comment out all this code first. All right, now since I didn't really do it in the proper way using another program to generate the assembly include file, I'm going to do this by hand, which is not a very safe approach. Because doing this by hand means that I have to look into the original structure definition and make sure I follow all the ordering and stuff like that. So this is saying that our member inside the complex is the first thing in the structure, therefore it has a 0 displacement from the beginning of the entire structure. Complex I equals 4 because the R component has 4 bytes. So the second component starts 4 bytes from the beginning of the entire structure. And the size is 8 because the second component is also 4 bytes long. Are we doing okay so far with these? It's not safe because if I make any changes to the C program, this doesn't get updated automatically. Unlike what we did last time, where if you make any changes to the .h file, the assembly code gets updated automatically. But since this is not the main point that I'm illustrating, I'm just going to shortcut it like this. So .global mode complex .text, and now we have to define the displacements. OEBP is 0. Return address is still OEBP plus 4, but now we have a return value address, and that's return address plus 4, and then we have the 2 parameters in this case. Now this time the parameters are also passed by value. Okay, what do you do when you pass parameters by value?
Make a copy.
Yep, there are entire structures on the stack. So that means when you calculate the displacement, you have to be more careful as well. So our first parameter, which is x, this is the easy one because return value address itself is only 4 bytes long. So this one doesn't get affected because of that. But the displacement to y, which is our second parameter, is going to be x, but not plus 4 anymore. But this time we have to say complex underscore size because it is passed by value. Are we doing okay so far with this? Now, is someone kind of curious why I want to pass by value instead of pass by reference in this particular case? It's because if I have additional functions like this, for adding, subtracting, and doing all sorts of other arithmetics with complex numbers, I can now put those function calls in place of x. If I pass by pointer, then I cannot do it, because you cannot. Well, I guess you can still do it. No, you cannot, because you cannot take the address of the value returned by a subroutine. So this is the only way to do it, so that you can actually have nested subroutine calls to take the place of your arguments. Are we still doing okay so far with this? No? Okay. You want me to illustrate it? Let me just illustrate why I want to do it this way, and I'll put it inside the comments. Okay. We are passing by value so that we can do something like this. Do you see what I mean? If I pass by pointer, I cannot do this anymore. All right, switching back to the assembly code. All right, we're almost done with the call frame. We only have one more item to deal with. Which item is that? The local variable result. So result is our local variable. It is old EBP minus the size of result. The result is in an entire structure, so we have to subtract the size of the structure itself from old EBP. And now we have all the labels that we need in order to continue with this program. Mode complex is the entry point. After the entry point, we do the usual thing: push EBP, move L ESP to EBP. At the end of this, we have to do a move EBP to ESP, pop EBP, and the return $4. Remember what the return $4 does? It returns just as normal, but it will also subtract 4 more bytes from the stack. It will add 4 more bytes onto the stack pointer, so that the stack is now 4 bytes. It has 4 fewer bytes than it used to. All right. Let's deal with this particular statement first. Well, obviously we need a mult instruction, because we have multiplication here and the multiplication here. Well, one of these has to go to EAX, because the mult instruction implicitly uses the EAX register. We cannot use MUL anymore, because MUL is only going to work for signed or unsigned numbers. Do you guys still remember, every time we use mul, are we using signed or unsigned? Unsigned. But this time, all of these are signed numbers, so we have to find the signed version of mul. If I remember correctly, it is imul. Imul long in this case. Let's confirm that. Yep, signed multiply, imul. My question is, why is it imul? What does I have to do with sign?
Steve Jobs invented it.
Sorry?
Steve Jobs invented it.
Like an iPhone.
Like
Steve
an
Jobs
iPhone?
made it.
Imul.
It's supposed to be a little I and a capital N.
Yeah. All right, so let's get back to here. All right, so we have to put one of these into EAX. I want you guys to tell me what to do here. Let's say I want to put x.r into EAX. What should I put here? But first of all, can I do it with one single instruction, or do I have to separate this into multiple instructions? Well, let's think about what is on the stack right now. Okay. I will draw this out using a text editor. Well, maybe not. Maybe I'll use a spreadsheet. spreadsheet works better in this case. Okay, let's try to figure out what is on the stack right now. Not that. All right. And we can close this one. Close. All right, so now we're ready. I'm going to use the same convention. You know, anything that's higher up has a higher address. Anything that's lower has a lower address. According to these symbols, which one has the highest address? Parameter y, which is the second parameter, has the highest address. But parameter y has two components, right? Oops. Did not intend to do that. Okay. Parameter y actually has two components. Which two components do you think y has?
R and I.
R and I, and of those two, which one has the higher address? I has the higher address, R has the lower address. Okay, because we define R first, and therefore R has a lower address. So when you look at the stack, Y is actually taking up 2 4-byte chunks. I'm only counting by 4-byte chunks because nothing here is taking up less than 4 bytes. And then the next thing would be X, but X has the same thing. It has I and R, like that. And then after that, what do we have? After that, return value address, exactly. And then after that, we have the return address from the call instruction itself. And then we have old EBP. And then we have our local variable called result, which also has an I component and an R component. Like that. So our call frame actually looks like this, with EBP pointing to old EBP here. So we have EBP pointing to the first byte of old EBP. Are we doing okay so far with this picture? Okay. So with this picture, and I want to access x.r, can I do that with one single instruction? Let's think about it. Let's think about what do we get when we have x using the based addressing mode. What is this going to give us? What's going to give us R? Now, but if I change the definition of the members, this may not give us the right thing. So we'll go ahead and just be redundant in this case and say we're going to add the displacement of the member R from the beginning of a complex number to x, which really doesn't do anything because complex underscore R is defined to be 0 in our code. But it's just good practice to kind of use this to self-explain what we are copying into EAX.
Well, it also allows you, if you make changes to the C code, it would be easier to adjust your assembly programs as your.
If I had used that approach, that makes it more easier to update. When I update the C code, it will also get updated automatically. Yep. But in this particular case, because I hard coded everything, it really does not it really does not matter. All right. Well, so we'll go ahead and deal with the other one. Y, we'll put it into EBX because if I remember correctly, IMOL and MOL cannot take a memory operand. It has to be a register operand. So we'll IMOL to EBX. Actually, EBX is a bad register to use. We'll use EBX. Now, after the multiplication, we only care about EAX because we are going to toss away the most significant 32-bit of the product. Because it's a 64-bit product, we cannot store the most significant 32 bits anyway. So EDX is really of no consequence to us. We don't really care about it. So we'll push this onto the stack. We'll push EAX, which is the only 32-bit that I care on the stack, and then later on I'll pop it back to use it later on, because we still have the addition to finish later on. And then the other instructions will be kind of like an exact copy of this, except where we had X, we will have Y in this case. Where we had
X, now you have, or where you have Y, you know X.
Sorry? Oh, it's this part here.
Yeah.
There you go. copy and pasting is bad. Sometimes you forget to change that one little letter, and the whole thing doesn't work. Okay. So after the IMO, after this instruction, EAX has the product of the second term, and I just have to deal with add it to the first term too. There are several ways to do this. You can pop whatever we have on the stack into EDX first, and then you add those two components. So you add EDX to EAX, and then we can store EAX into result.I. So that's a single move instruction, EAX to, and then the same thing, result plus complex underscore I, EBP, and that will store the product, is the sum of the two products into the I member of the result. Are we doing okay so far with this? Because the next line is going to be about the same thing, except we have to do a subtraction instead of an addition, minor differences. Are we doing okay with this? Okay. So now I have to be even more careful because copying and pasting is bad. 20 to 29, copy it here. Oops. 20 to 29, 20 to 29, and paste. Go. So for this one, I'm going to calculate the second one first because the subtraction instruction, well, either way is fine. We'll do it the same way. We'll do it in the same order as in the C code. But instead of having an add instruction, we have to use a subtraction instruction this time. So we have to use a subtract long instruction. And then I have to be careful which one is subtracted from which one. I think I got it reversed in this case. So we have to change the order like that. And we are storing this into the R component of result. We still doing okay? And now we have to return the result. Now, how do we return the result? Result itself is a local variable. I cannot pass a local variable back to the caller because a local variable is destroyed after the subroutine returns. So what I'm doing here is I'm making a copy. I'm copying result as a structure to the space that is reserved for the return value. So we are doing the mem copy thing. And mem copy wants to know how many bytes we are copying. That's the last parameter. In this case, it is $complex size. And then we have to specify, I think, the source. The source in this case is the address of result. Okay. So we push EBP first, and then we can do some calculations on top of the thing that we just pushed on the stack. So we're just going to push, just add L result, which is the displacement from where EBP points to the first byte of result to whatever the stack pointer points to, which is EBP. Are we doing okay so far with these two instructions?
Is it EBP or ESP?
It's ESP for the second instruction because I'm adding result to whatever I just pushed on the stack.
Right, but with your predefining result, does that take into account what you've just added to the stack, the displacement? Or
are you referring to the add L instruction?
Right.
Well, I just pushed EBP on the stack, and I do want to add the constant result to whatever I just pushed on the stack. There's a comma behind the I-beam.
Oh.
Another Apple product, the I-beam. We doing okay so far with this? Somebody at Apple probably went through the entire dictionary, locate all the words starting with I, and go through send in tons of paperwork to the PTO, USPTO, so that they can reserve all those names as trademarks.
You have to pay
All right.
5 cents every time you use an item.
Yep. All right, so the third component is really the destination address, and that's the easy one. Because the destination address is actually one of the components on the stack right now. So it is return value address relative to EBP, and we just push that on the stack. And then we can use the mem call, mem copy call, just like that. And then we can readjust the stack pointer, add 8 to ESP, oops, 12, to readjust the stack so we free up all the resources. And then the rest of the program, just works the same way as before.
All right, let's prove it.
Let's make it. Yeah, let's see whether it works or not. UCC-G. Okay. Complex.c, and then we have mult complex.s, and it works without crashing.
Now,
I think, yeah, go ahead.
does it prints all that?
Did you want to step
Because when we hit those marks, would it still not? Would it crash if there was still anything left over? Or is there a way to check it, or does it really matter if your stacks are balanced and everything at this point?
That's a good question, and I think most people have a question about this this return instruction here. Why do we have to free 4 bytes in addition to the return address itself? In other words, wouldn't it be okay if we just do it this way and rely on the caller to free up those 4 bytes as well? So let's go ahead and do it again. Oh, it works.
I have a quick question.
Yep.
So you didn't specify an output file for GCC? Does it just automatically make complex?
Oh,
Or is that the whole?
you're right. It's a.out.
Okay.
My bad. A.out will probably crash. Yep, gives you the wrong value. Okay, if I fix it, then it will
Interesting,
work.
because it put the original R's in I, and then you got some weird value in R.
Right, because it's off by 1. Everything is off by 1.
Right, 1 byte. Okay.
On the other hand, if I keep the $4 here to deallocate the 4 additional bytes,
Still got a problem.
it's still wrong. I'll figure out this one and then report back next time. I know there's something interesting about how it uses the stack. Well, we can try the other way too. We can try this way. I don't think it's going to help because it doesn't really adjust the stack pointer itself. So we'll say add $4 to ESP. And then do a jump to whatever EX points to. Effectively, it's the same thing as a return $4. And it's still wrong, but that's not surprising. Yep.
Can we figure out why it's wrong?
Well, I can show you how I would do it.
Yeah.
Okay, to figure out why it is wrong. The way I would do it. And I already compiled with a -G, so I can use gdb a.out to debug the program. And I will put a breakpoint on line 33, run the program until it gets to line 33, and single step into the subroutine. Now inside the subroutine, I can just keep single stepping until we get to the very end here. Let's see, move L. Okay, so what we want to do, before the pop out instruction is to make sure that we have the right result in our local variable result. Because if we get the wrong thing in the result, then obviously nothing else is going to work. Okay, so result has 2 4-byte items, and it is located at EBP plus the offset of result. That doesn't work because it doesn't like result. Result is it doesn't like that either. Okay, that's fine. I just do the calculation by hand. Right? Handy. EBP 8.
This is how my homework normally goes.
Okay, where am I here? I'm right before the top EDX instruction. Oh, I'm not done with the calculations yet, no wonder. Okay, I still have to go through the calculations. And, okay, this is the part where it does the mem copy. So I think we should look at it again. I must have missed something really, really obvious. Okay,
I mean, it almost looks like we're off by 1 byte of how
off
we're
by
storing it.
one chunk.
Yeah.
Okay. So we have push EBP, move ESP to EBP. Oh, I forgot one. Okay, can anyone tell me what I just forgot?
You didn't put space for the local variables?
Sorry?
You didn't allocate space for the whole.
Yep, exactly. There we go. Oops. Yep, that's a big oops. All right. GCC again. We got out. And it is.
That's right.
It's wrong, but this time it can be. Well, one of them is right, and the other one is wrong.
Right, but we used to get the 8, so that's.
Okay, it's the R component that is wrong, so let's go ahead and take a look at the source code. And okay, it's this part here that is wrong.
It's the one you copy pasted.
Yep, copy and paste, bad.
Is it because your EDX should be swapped?
Where's the, oh, subtract down there.
Yeah, this is the R component. It is pushed on the stack. It is popped into EDX, and I'm supposed to subtract EAX, which is the product of the I component, from that. So that seems right to me. Okay, use GDB to help debug it. Using GDB is almost like cheating. It makes debugging so much easier.
Sounds like an ad for GDB.
If I were a politician, that would be my platform.
I come with GDB.
Yeah, exactly. Well, my first thing to do is to introduce the use binary numbers instead of decimal numbers, starting from kindergarten. And I think I'll get all the kids to support me, because the multiplication table would be trivial in that case. Let's see, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1. Mom, I'm done with the multiplication table.
Well, the thing is, it probably would work because they've proven that children adapt and pick up languages naturally. Where
Yeah.
once we're settled in our brains, by the time we're older, learning language is a pain in the butt.
Yep, exactly. Okay, so I'm gonna put a breakpoint here, to right after I do the calculation. And let's see, did I store it into R? Yep, so put a breakpoint at line 41, run the program. EAX is -6. Okay, so I did the calculation wrong for some reason. All right, so this is a confirmation that I got it wrong at this part of the program.
Should be stored.
We are subtracting EAX from EDX. and EDX is the R times R part, and then EAX is the I times I part. What did I do wrong here?
Should be right, so are we pulling the wrong numbers to EX and EX dot R?
Oh,
That's EDX.
okay, that's it. Copy and paste.
For read stuff.
There we go.
Wait, go back. I
Mhm.
missed what you changed there.
Oh, EDX.
I got it.
Okay. All right. So got the program done. We just illustrated how to return the structure, and also along the way, I accidentally made a few bugs and fixed them all, and also illustrated how copy and paste is really bad. This is actually not the worst thing I have done. I know this is assembly language programming. There was one architecture that has two instructions. They take the same kind of operand, but the instructions are only different by a little bit. One is called in, and the other one is called in 0. Okay. Now the difference between these two instructions, since we're already programming in assembly, I can kind of explain what the differences are. In 0 assumes that the high address of the I/O location to be 0. In, on the other hand, assumes one other register gives you the high part of the address. In other words, they take the same parameter here, except one assumes a 0 for the high byte, the other one assumes the high byte is stored in another register.
So
Okay.
basically the difference between it expects a 16 byte number and the other one's pulling a 32.
Something like that, yes. But the two instructions take exactly the same operand. So if you use the wrong instruction, but have the operand specified correctly, the assembler doesn't know the difference. It will just go ahead and use a uninitialized register to supply a part of the address that you're trying to access. Okay, and I made this mistake once, in one of the assembly code, and this is for an embedded processor. Okay, does everybody understand what is an embedded processor? It's a processor on a circuit board that goes into applications like industrial settings and big machines and equipment and stuff like that. It doesn't have a console. It's not like a PC. And this is also a part of the firmware. Okay, does everybody understand what is the difference between software and firmware? And we are not talking about tofu here. Okay, software is what we are doing here. Firmware is really software, except it is not supposed to be changed easily. Okay, it's kind of like a BIOS on the PC. It is software, but it is supposed to stay the same most of the time. With these older circuit boards, there's not a whole lot of debugging facility. There's no GDB on it, and because it's actually okay in the good old days, the firmware is actually stored on EEPROMs. Has anyone seen an EEPROM chip? Okay, some people have, and most people have not. I'll show you a picture of an EEPROM. EEPROM, and go to images. That's a very typical picture of an EEPROM. EEPROM stands for electrical, EPROM, electrical programmable read-only memory. Okay, which is an oxymoron all by itself, because it's read-only and yet it is electrically erasable, electrically programmable. And there's double EEPROM too. EEPROM, I think that's electrically erasable programmable read-only memory, which is even more weird. Okay, so the question is, if you have a ROM which is supposed to be read-only and yet it is programmable, how do you reprogram it once you program it once already? Well, that's why we have a little window here, right? You expose it to ultraviolet light for 15 minutes, like really intense ultraviolet light, and that will erase the content of the ROM, and then you can reprogram it. That's how you refresh. That's one cycle of programming. And I wrote this bug into the software that runs from one of these chips. So the development cycle is rather long. Now I already had like 8 or 16 of these chips next to me, so I don't have to run to the eraser every single time and spend 15 minutes to erase it every time I want to change the program and test something. But you also have to remember, I don't have GDB. I cannot specify a breakpoint and say, let's stop here and single step from here on and see what the program is doing. The only sign that I can use outside of the controller to find out whether it is doing the right thing or the wrong thing was an LED. Is the LED lighting up or not? And every time I change the software, I have to take one of these chips, go to the programmer, program it, and then remove the chip that's already on the board, plug that chip in, power up the board, look at the LED, oh, it's still off, And then once I use up all 16 of the EEPROMs that I have on hand, I have to take all 16 into a little tray, put the tray into the UV eraser, and then wait 15 minutes until it is erased, take it back out, and then do the whole thing again. You can kind of imagine the productivity back in those days when we had this sort of thing. That was absolutely the worst bug I have written into software.
You made that face right there. You made that face right there.
That face, yeah. Well, that was my worst, but there was something worse than that, that was written by somebody else. It had to do with, since we're digressing, we might as well digress more.
It's called Windows. Is it called Windows?
No, it was, okay, somebody did not read the data sheet of a processor. It's the same processor. It's called the Zilog Z180, which was used in the original Game Boy consoles. But somebody did not read the specification and did something that the specification did not say what would happen. Okay, the specs sheet says you have to do it this way, but it did not say what would happen if you do it the other way. So whoever wrote that software, and I know exactly who that was, I just do not want to name the named person. So that person decided to use the other way because he did not read the instruction, the data sheet, and it worked for the longest time. One day we had customers calling in and say, you know what, your software is not working anymore. We just switched to a new batch of the same board using the same processor, and it's not working anymore. So we found out the common part of of what works and what doesn't work. It had to do with the batch number of the processor chips. So everything before a particular batch number worked just fine. The old ones worked just fine. The new ones using the new batch number doesn't work anymore. So as it turned out, they changed the process of manufacturing the chips, and therefore they changed the transistor sizes and whatnot. And that changed the condition. As it turned out, when the other person was doing the instruction in the wrong order, it caused a race condition. Does anyone know what is a race condition in electronics and programming? It means you are starting up two parallel processes where whoever gets to the finish point first will decide the result. Okay? In other words, in the old chip, okay, for some reason, one is always winning the race. One side is always winning the race and causing it to give you the right result. But the new batch of processors using a smaller transistor changed the internal timing of the processor. So in the race, the other one wins this time, giving the wrong answer. So it took me a little bit of time to find out what was happening, and the marketing manager was breathing down my neck the whole time, saying, "When is it done? Tell us, when is it done? Because customers have called and we told them this will be done by a certain time." And I just turned around to him, and this is a pretty big guy. He played football back in college, and I just turned around and told him, it's done when it's done. I think he just popped a few fuses when I said that, but it was true. I cannot get it done any sooner than getting it done. And eventually, I think the sales manager came in and just said, "Leave tag alone," because keep asking him is not going to make it any faster. I got it fixed in about 2 days. It was fun.
But that's when you tell them 3 weeks. You pull the old Scotty on them. And they're like, I need it in 1. You're like, okay.
No, I want the raise first.
Raise, free vacation.
Yep. So anyway, so are there any questions at this point? We also missed some other things, other than returning a structure. There are just a few things that we have to finish up, but you guys probably know how to do that stuff already. How do we deal with arrays and pointers and structures, all of these things, together? Well, let's deal with arrays first. Okay, first thing first. Well, arrays are actually pretty easy to deal with. So we'll go ahead and use this as an example. We have a certain type, uppercase T, whatever it is, and we have an array R, and it has 100 of those particular items. The question is, how big is that array? Well, first question is, how big is that array? The size of the array is really the size of each element times the number of elements you have in the array. So that's pretty easy. The second question is, if I use R bracket I, how do I do this calculation? What is the address of element I in the array? Well, as it turns out, we can do it this way. This is R, which is the array, but you can treat an array in C as an address of the element type. But that's not going to help you much, because I have to cast everything to a char pointer to do the calculations. Once I cast R to a char pointer, I can now use the normal calculation. So I'm multiplying I to the size of T, and then add these things together. So the right-hand side, the expression on the right-hand side will give you exactly the same quantity or the same value as the left-hand side. Question?
Well, basically, so on the right side, you're taking the original starting point and saying, hey, we're going to do it by char pointer. So you're reducing it. While on the right side, you're actually making I the size of the element, whether it's an int or whatever, and then multiplying. So it's kind of like seesawing the side of the equation and still getting the same result.
Correct.
Okay.
This one is just, this is high-level stuff. Okay, this is high-level stuff. Because the compiler knows the type of the element inside the array. So it automatically knows if you want to access element I, it has to multiply I by the size of the element to get to the first byte of that particular element. The right-hand side translates to what we need to do in assembly. Because remember, in assembly language programming, we don't have types, we don't have structures. So we have to do calculations on a byte addressable fashion. So that's why the right-hand side is what we need to do in assembly. So here's the question. Can we do the right-hand side in assembly? Well, what does it have? It has, well, first of all, we need to know the size of an element. Well, that's kind of essential. We have to know the size of an element first. We have to know the index, okay? But that's natural too. If you want to access a particular element in an array, you have to give me an index. Which one do you want to access? We know how to do multiplication. That's just the mul instruction. And we also know how to do the addition right here. Okay, so we should be able to do all this stuff here in assembly. Are there any questions? No? Let's go ahead and extend our complex number program to come up with an initialization subroutine so we can initialize an array of complex numbers in a certain way. Is that good? You guys are kind of... All right, so we'll go ahead and do this. I'm just extending this program to initialize an array of complex numbers. So this will be a void point. It will be a subroutine that returns a void, and we'll just say init complex array struct complex. So this is pointing to the array. So we will have P array, and we'll give it an integer, unsigned int, which is n, the number of elements in the array. And then inside here we have our index I, and we'll initialize I to 0. While I is less than n, do the following. We'll just say P array bracket I dot I equals I. P array I dot R equals I. It doesn't matter. Negative I, whatever. And then I gets I plus 1. And that's my initialization subroutine. I want to implement this in assembly. Okay? Are there any questions about what this subroutine is going to do? Not really. We can test it. Okay? I don't even need a printf to make to test this part. So in my main program, I'm going to say struct complex and an array. We'll just have 4 elements in this case for testing purposes. And after the usual code, we'll just add this part here, and we'll say, what was the name of the subroutine? Init complex array. Init complex array. And we'll give it array, and we'll give it 4, because we have 4 elements in the array. We doing okay so far? Just with the C code. This is not in assembly yet. GDB a.out. And all I really need to do is to put a breakpoint on line 49 after the call is finished. Run the program, and I can just go ahead and try to print array. Is that what you're expecting? Kind of. I mean, that's what the subroutine is supposed to do. It's supposed to initialize the I member and the R member, and one is going to be the positive side of the index I, and the other one is the negative side of the index I. Are we doing okay so far with the C code? So the next question is, how do we do this in assembly? So I'm going to comment out this code in C and try to do it in assembly. I'm just debating, whether to start a new file to do this or reuse the old file. I think I'll just start a new file. 22 here. Init complex array dot css paste. Okay, we have R first, and then we have I. It's the same thing as last time. I think I should just go ahead and copy and paste from the other one. Oh, I just have 2 more lines. 1 more line. And now we can go ahead and use comment to comment out all the C code. But before we do that, we have to allocate for the storage. So we have to start with OEVP. Then we have return address. And then we have p-array. Because this time we are not returning a structure, we don't have the return value address on the stack anymore. This is just return address plus 4. And then we have n, which is p-array plus 4. On the negative side, we have local variable I. So we have I being OEVP minus 4. This 4 has to do with the size of I itself and not the size of OEVP, because it's on the negative side. Okay, the entry point is already done. Push out EVP, move ESP to EBP, and this time I'm not forgetting to reserve space for the local variable, which I forgot last time. And when we get out, we have to move EBP back to ESP, pop EBP, and then just do a normal return. And from here, we are just doing a line-by-line translation. I is initialized to 0. A single move instruction can do that, because I is just something that's living on the stack. And next, we have to implement the loop. We have to compare I to n. If I is less than n, then we have to stay in the loop. If I is greater than or equal to n, we get out of the loop. We cannot do a comparison between I and n directly because they are both memory operands. So we have to move one into a register first and then do the comparison. It's also going to be helpful to say this is while begin, because we have to come back to this point from the end of the loop. And we might as well just do it here as well to jump to the beginning of the loop. And also put a label here to mark the exit of the loop. All right, so now we have to do the comparison. Just move one of them into a register. It doesn't matter which one you move into a register. I is now in the register. And then we do the comparison. You have to remember, when you do the comparison in assembly, you want to flip the order from the original items. So in this case, we want to put n, EBP as our first parameter, and then put I as our second parameter. But I is now in EAX, so we only have to specify EAX. The conditional branch is to get out of the loop, because we automatically fall into the loop when the condition is false. So that means we are not checking whether I is less than n, we're checking whether I is greater than or equal to n, or if you prefer, not less than. So in this case, it is JNB because it is unsigned. If I is not below n, get out of the loop. Is that okay so far? Because we have to flip the logic to specify when do we get out of the loop. So if that is true, we go to while exit. If not, we're going to do the following. All right. So this is the actual meat of this particular sample program, because all I want to do is to illustrate how do we do indexing. In this case, there's a little bonus, because after we do the indexing, we also have to access a particular member of that particular element. But it's really not, that much more work. All right. So let's go ahead and deal with the left-hand side first. Typically, we deal with the right-hand side first, but this time I'm going to deal with the left-hand side first. How can we access, p array bracket I dot I? Well, we have to start with p array. So let me ask you this question: what am I actually moving into EAX here? If I want to comment what EAX is at this point, what is it?
The structure.
It is the address of the first element of the array. Or simply, it's the first byte of the entire array. Okay? That may not be very useful at this point, so I'm going to leave the instruction here for now. Because I have some more work to do before this becomes useful. And that being, what is the offset from the beginning of the entire array to element I of the same array? I have to calculate that offset first. How do I calculate that offset? We have to compute I times complex size. Okay. So once we know what we are supposed to do, it's not too hard to do it, because we have to move I EDP into EAX.
It's already there, isn't it? Or
It's
we're just covering bases.
Yeah, I'm just covering bases, because it's already here because of that instruction. But since I'm not trying to optimize the program, so every single time I access I, I'm just making the assumption that we still have to copy that. So I is there, and then dollar complex size, we can put it into, say, EDX. Do the mode long instruction with EDX. So now after this, EAX is the number of bytes from the beginning of the array to element I of the array. Is that okay so far? Okay. So with this one, I can just put it into EDX, so I can add the numbers. So EDX points to the beginning of the array. So when you combine EDX and EAX, what do you get? When you add EDX and EAX, what do you get? You have the beginning of the element that we want to access, right? But do we want to access the beginning of the element, or do we want to access a particular member of that element? A particular element, okay? A particular member of that element, okay? So that means well, we are calculating the address of the left-hand side, but not the value of the right-hand side. So maybe I should do the right-hand side first. The right-hand side, I will just push the right-hand side on the stack. It's just that. Is that okay? Because the right-hand side is just really saying, oh, what is the value of I? Well, the value of I is I parent EBP, because that's our local variable. It's living on the stack, and we just push it on the stack. Now here's the trick. How can we combine all of these operations into one single one using the cisp operation? We use a pop-out instruction. In other words, we are taking the right-hand side of the assignment operation and pop it directly into where we are supposed to store it. Now the question is, how do I specify where we are supposed to store it? Now, we know that EAX and EBX are useful, right? And we want to add those two together to become the address of the beginning of the element that we want to access. Now, if you want to be very careful, you can also say (1) to make sure that your scale is 1. But this is not what we want, because we want a particular member of that element. So that's why we have to add the displacement to that member on the top here. Are we doing okay so far with this sequence of instructions?
Is that defined earlier?
Yeah, it's defined at the beginning of the program. Okay. The other one is about the same, except it's the negation of I, so we will do the same trick as usual to calculate the displacement of I. So for this one, the right-hand side is a little bit tricky, but the left-hand side would be the same as last time, or just about the same. So this time we'll push a 0 on the stack first, and then we'll use a subtraction instruction after that. Oh, maybe not. I'm trying to be lazy. I guess I cannot really be too lazy this time. Okay, I guess we do have to initialize EAX, and then
Then subtract.
yeah, but then I need another push instruction. So I can do this first, and then say subtract. No, I cannot. There's no quick and easy way here. We'll just do it the hard way. Is that okay? We initialize EAX to 0, and then we subtract I from EAX. Therefore, EAX is now negative I. We push negative I on the stack, and then we can reuse almost the same code as last time.
It's cheap.
It's cheap, yeah. So now we can just do the same thing here, which is starts from here, line 30 to line 36. And we just have to be very careful at the end to use the R member instead of the I member.
If you're going to count it manually, when you copy in DI, you can just do Shift-V, and it'll select the line right appropriate.
Say again?
If you use Shift-V, it'll select the entire line every time you move the cursor up.
Oh, Shift V,
Shift-V,
V.
V for volume.
Oh, okay. Uppercase V.
I guess so.
Try. Oh. I did not know that. So it automatically selects, so when you type Y, it automatically yanks all of those highlighted lines.
If you type Y or if you put like a colon, it'll automatically insert it into the.
Got it. Okay, so it's basically an internal way to keep track of the line numbers, so you don't have to count the lines. Okay, very cool. All right, so I think this program is all done. Oh, except I forgot to increment I, so this becomes an infinite loop. It's an infinite loop at this point. Yeah. So I, EP, that's the increment, and that should be it.
There's actually an increment instruction, isn't there?
Yeah, there's an increment instruction, but since I want to minimize the number of instructions to use, I'm just using the instructions that we know already. All right. Any questions at this point? No questions? Okay. So we'll give it a try. Just have to add one more thing here, init array complex array.s. Wow, I didn't make any syntax errors. Doesn't mean the program is going to work. Put a breakpoint on line 32, 52. And print array. Wow, it works too. Okay, I don't trust myself. I don't trust myself. I want to make sure that in the C code I did comment out init complex array, and I did. Oh, wow.
Good job.
I am surprised. Usually, if I write, anything that long, typically I'll introduce a few bugs along the way, and then I have to go into the GDB
I think it's
and
because
fix
the
the
buzz
bugs.
of the previous one you were watching for him, so you caught him.
No, I wasn't being any more careful than before.
Well, except you did remember to create space for the local variable.
Yep, that was the problem. Yep. So, are there any questions about what we just did in today's class? No.
Sounds complicated.
I can't remember what I was about to do. I'm having a moment here. I was thinking about my CISP 453 class, and it has to do with assembly programming. In my CISP 453 class, which this semester is the last time that class is going to be offered, so it won't be offered ever again on this campus. It's systems programming in Linux or Unix, and in my class yesterday, I was explaining how I wrote my own real-time kernel, and it's all written in assembly. There's a whole bunch of push and pop instructions, but I could not remember what I wanted to talk about in this class. I can only tell you this much. The real-time kernel was written all in assembly, but everything was written in a way that the API or the application programming interface is callable from C. So the entire library was written in assembly, but it was intended for C programs. So now you can write a C program and still have multi-threading using a processor that's about yay big. It costs you about $12 or so. And the real-time kernel itself is 2 kilobytes long. That's the entire kernel, 2 kilobytes. The device itself has 128 kilobytes for program space. So that was, I think that was fun. It was fun writing that particular real-time kernel. It was my summer project for that summer.
So,
Yep.
extra credit?
Translate that real-time kernel for the i386 architecture, right?
And then that's extra credit?
Do you really need it that badly?
I don't know, it depends on how I did on the exam.
Ah, the final exam.
No, this one.
This one?
All
Alrighty. Okay, well that's the end of today's class. There's no new homework assignments, so next time we'll probably have structures in our homework assignment.
So you need these back?
No, I don't need yours back because you should have a grade.
Yeah. For the first
Yeah, you have a grade, so I don't need yours.
okay.
Yeah, three people in the class, probably do not have a grade because I'm missing the first page. Are you one of those? I think so. Okay, let me check your name. Yep, you're one of them. I'm gonna scan it and then I'll return it on
Grade only the
Tuesday.
first one.
I only graded the first and second.
I had a question about why I got only half credit for.
Because it's supposed to be $1. I mean $1L1.
This is effectively the same location.
Is it? It's not the same location because $L3 plus 4 is going to specify the address of probably this compare long instruction.
He says he's looking at each one. I don't know.
L3 is here.
Because this is what we're
Now, if you put the right instructions, like he did, where he put the right
comparing
number
to.
on the wrong
Comparing to what the stack point is pointing at, but not exactly there, but 4 bytes above what ESP points to, and that turns out to be L1, the return
But he
address
put it on the
of
low end.
the call G instruction.
I know what I did. I was looking at it on the stack side.
Yeah.
I was trying to tell it L1, but I don't know why.
I think you have to flip it because ESP does point to L3, but L1 is actually on top of that, not below it. Because this is the first one. Yeah, but okay, which side is high address? This way or that way?
That way. Because
That's
L1's
high
gonna be on
address?
first. Yeah. That's
If
just,
that side is high address, you already know it's L1 because ESP plus 4 is L1. So I don't understand why you wrote down L3 plus 4.
I don't. It made sense to me. I promise you that I meant that to be this location. I was saying, oh, I got to shift. Yeah, that's.
Aww. The $sign gave you partial credit, so.
Yay! Oh, I got the $sign right. Thank God. Why did I say L3 plus 4?
Yeah, you're not the only one too. There were like 2 or 3 other people, who also gave me L3 plus 4, which was puzzling because
that was
most
me.
what?
That was me also.
That was you also.
Yeah.
But that's puzzling because I can see people using $L3, but not $L3 plus 4. I mean that part just kind of.
Why did I say? Because I said.
Yeah, that was why.
I was just thinking on